Alright, next up I want to talk about one of the data structures that you're going to need for homework 4, which is now posted. So in C, we have two kinds of data structure that are provided by the language. The first kind of data structure that's provided by the language is arrays, and the second is structs. And we just talked about those two kinds of data structure, but an interesting part about those two data structures is that those two data structures end up being sufficient as building blocks to build pretty much any other kind of data structure that we frequently use in computer programming. In fact, basically any kind of data structure that we ever use in computer programming. So most programming languages provide a little bit more than that. In their standard library. Specifically, two very common structures that pretty much every modern programming language provides are a variable size sequence which is something that we don't get in C. An array is not a variable size sequence. It is an unknown size sequence. We can have an array of length 5 or an array of length 10, but once we have an array of some particular length, it's that length forever. If we want to add an additional item to an array, either we have to have allocated extra space at the beginning, or we have to allocate a completely new array and then somehow use the new array instead of the old array. So most languages have some way to have a variable length array, and that's something that would be nice to have. The other thing that we almost always have is some sort of key value map data structure. In Python, those are called dictionaries. In C++, we call it a map. In other languages, we might specify exactly what kind of map. So we have a tree map or a hash map. And frequently it's worth differentiating between different kinds of map data structure. A tree map and a hash map have different performance properties and slightly different interfaces, but most of the things that you can do with one, you can do with the other. And so the sort of minimum requirement for utility in a modern language is to have some sort of map. C++ has neither of these things, but for homework 4, you're going to get to build both of them. And I want to go ahead and talk a little bit about variable length arrays. We'll talk about maps more in next week's lecture, but for this week's lecture, we're going to cover the design of variable length arrays. Since you're building them for a homework, I'm not going to talk about the code for it, but I'm going to talk about what the plan is. So we need normal array functionality. And the idea is normally we can index an array, and we can either read a value from a position in the array. So if we want to get the element in slot 5, with a normal array we can do indexing syntax. If we're going to write a variable length array in C, there's no way to sort of overload the array indexing syntax, so we're going to need a function that takes an array and an index and reads an element from the variable length array. Similarly, we want to be able to put things into the array, so we'll take an array, an index, and an element value, and we'll stuff that element into that slot in the array. So we need to preserve the functionality that we have with arrays by default. And then sort of the absolute minimum to demonstrate that we really have built a variable length array is a pushback operation. So if we have an array 1, 2, 3, 4, and then we say push back and pass our pushback function, that array 1, 2, 3, 4, and then the number 5. That's going to give us the array 1, 2, 3, 4, 5. The variable length array 1, 2, 3, 4, 5. And then the other requirement for having an array for having a variable length array in C that we want is we want to have our arrays remain contiguous in memory, so we can still do a normal for loop. And we even want to be able to have the place where we're storing the data actually be an array that's accessible, so we could take that array and pass it to a function, which would then do some sort of read-only not or operation that mutates elements but doesn't try to resize the array. And we get this sort of backwards compatibility with arrays as they exist in C anyway. This eliminates a bunch of options that are frequently used for sequence data structures, like we can't use a linked list because that doesn't give us an array. But it's something that we can work with, and there's a good solution to this. So in order to actually do this, we're going to just go ahead and start with a normal array. And when we push n, so this is a pretty simple solution. We start with a normal array, and then the pushback operation will just allocate a new array of the size of the old array plus 1. We will copy the items from the old array over into the new array, stick the new item onto the end, and that actually works great. We're going to successfully have a variable length array. Unfortunately, there's a problem. If we start with an empty array, or we start with an array of some length, and then we push n items onto the back of the array, that whole operation is going to take n squared time. Every time we push an item onto the array, it's linear time. We have to copy the complete array. So if we do it 10 times, then we have 10 linear operations. If we started with a length of 0, then that's going to come out to, well, half of 10 squared is 55, a little more than half. Euler's formula, I think. In any case, big O notation, as gets covered in discrete and algorithms, this is a big O n squared operation to push n items onto our array, and that seems silly. We should be able to push n items in n time. So the solution to that is actually pretty straightforward. We just allocate more space than we need. If we allocate, for example, 10 slots instead of 1 slot, then the first item that we push requires a reallocation, but then the next 9 do not require a reallocation. Unfortunately, if we grow arbitrarily, picking a fixed value like 10 as the amount extra that we're going to allocate doesn't change the asymptotic complexity. It's still going to be big O n squared to push n items once we get into sufficiently large n. So instead we're going to do the following plan. So we never allocate an empty array. That's just a waste of time. If an empty array is requested, we're going to allocate space for 4 items, or 2 items or something. So then if we are doing a pushback Then we don't need to reallocate if we have empty slots. We keep track of how many slots are full, how many slots are unused, and we use the unused slots to satisfy sort of requests to push back. We'll use that space. When we run out of empty slots, then we do have to reallocate, but instead of reallocating just one slot or a few slots, we're going to double the size of our array. So if we have a variable length array of 10 items and we've only allocated 10 slots, we're going to reallocate an array of 20 items and then use one of those 10 free slots as where we push back. Now, in order to actually do this, we need to track both size and capacity for our data structure. Now, in order to track size, which is a useful thing to track for an array anyway, and to track the array itself, we're going to need to have a struct with multiple fields. And if we want to track size and capacity separately, then that means we're looking at 3 fields: the array, the size, and the capacity. But with all that work, we can now insert n items in n time. Okay, so imagine for a moment we're going to start with an array of length 4, and then we need to push back 10 items. I thought I was going to sneeze. I'm sure I'll sneeze in a second. So we're gonna start with initial capacity 4. We'll start with an empty array, an initial capacity of 4, and we'll push back 10 items. So push back 1 through 4 is 4 operations. Push back 5 doubles capacity to 10. So 4 operations to copy plus 1 operation to push back equals 5. Push back 6 through 8 is 3 operations. Push back 9 doubles capacity to 16. So 8 plus 1 is 9. Push back 10 is 1 operation. Total is 4 plus 5 is 11, plus 3 is 14, plus 10 is 24. So that's about 2 times n operations, which, if that's accurate, would tend to hint that we're looking at a sort of complexity of n. Let's try again with 100 just to see what happens. So here we're just going to look at how many times do we double. We double at 5, 9, 17, 5, 9, 17, 33, 65, and that's it. We're done doubling at that point. So each one of those doublings is going to have to copy sort of this number minus 1 items. So I'm just going to pull up my calculator over here. We have 100 insertions for the actual pushbacks, plus 64 plus 32 plus 16 plus 8 plus 4. We get about 224. So again, we end up having to copy everything about once. Like on average, well, as a simple estimation, we're copying things. And you can see that it was 24 before. So we had so we went from 24 for an n of 10 to 224 for an n of 100. This makes the 2n estimation look plausible. We really are able to do insertions not in n squared time and not in n squared operations, but in 2n operations, and that's big O of n. An interesting fact here inserting one specific item may still take linear time rather than constant time. And the traditional way that we analyze this is thinking about one insert at a time, and then we talk about amortized constant time. But I like talking about inserting the sequence better, because then we don't have to worry about like explaining amortized analysis for asymptotic complexity. So in a variable length array, and specifically in C++, this is a vector. In Java, this is called an Arraylist. It's called other things in other languages, but C++ and Java both have multiple sequence types, so their naming at least means something. We have a struct. In Java, it's a class, but same sort of thing. There are 3 fields. We have data, which is going to be a pointer to an array of elements. We have size, which is the number of elements in the array, sort of the logical variable length array. That's how many items are in it. And then we have capacity, which is the actual allocated size of our data array. That's how much we mallocked, or how big that's how much memory we've actually allocated for data elements. And it always has to be greater than or equal to size. That's just an invariant. Otherwise, we wouldn't have enough space to store the items that are actually in the array. Non-resizing operations can access the data array elements directly, just through the normal mechanism of array access. To append, we insert into free space, and then in our C implementation, if we run out of space, we're going to call Realic to double the size of the array. And Realic is just a helper function that does a allocates a new space, copies the old data over, and there's the possibility that Realic could be implemented in an optimized way that it doesn't actually do the copy, but in practice it copies. It allocates new space and then copies. And the other thing here is, in order to get the performance benefit, any multiplicative factor will work Resizing. I suggest 2 because it's simple. But C++ might use e.g. 1.5 as its thing. So it would start by allocating an array of size 4. Then the first time it has to grow, it'll reallocate 6. The next time it has to grow, it reallocates 9. Then the next time it has to grow, it reallocates 9 plus half of 9 is 5. So we get 14, then 21, and that might be more efficient or might not be. To really figure out, you'd have to benchmark, but it's a little easier to multiply by 2. So that's the story on variable length arrays. Good luck getting started on homework 4. We'll talk about the other thing, which is going to be hash tables in a future lecture video.